again, we start with kind of the ones that are not overly challenging so that we kind of get the feel for it. We'll work our way into it. In fact, the first one is going to be one we've done a couple times because we've already looked at it, but going to use it to kind of give us an idea of when I know I'm down the right path and when I know I'm down the wrong path. So in the words of Yogi Berra, when you come to a fork in the road, take it, which means when you're doing U substitution, try something, okay? Try letting U equal something. And if it doesn't work, go back to your fork in the road and take the other way, okay? So what's going to happen on your assignments, and some of you it's going to bother and some of you it's not, you might start into a problem and realize you have taken the wrong path. And that's okay. You don't have to erase it. Leave it on there, cross it off, whatever. Just go back and let U be something else, okay? So a lot of our conversation today is going to be about what do we pick for U? What does it look like when I know I'm down the correct path versus the incorrect path? We did this one yesterday, okay? But I want to use it to show you a wrong path. At what point do I realize that I've done this incorrectly? Okay, so whether you put this in your notes or not, I'm going to start by showing you the wrong path. Yesterday, when you were handed this problem, next to it said let U equal, and it told you directly which of those things up there to pick as U. There are several functions that we could pick. You have the function sine of x. You have the function cosine of x. You have the function e to the cosine of x, right? So how do I pick one of those? Well, until we get the hang of this, you might have to just guess and check. So what if I were to let U equal the sine of x? Seems like a decent choice, right? It's a basic function that I know the derivative of. That's one of the things that we want to know, is that I can take the derivative of U. So then as I'm doing this wrong path here, that means my problem would now look like U times e to the cosine x dx. And our steps from yesterday told us, okay, now come over and find du dx and solve for dx. Well, the derivative of sine is cosine. So solving this for dx, we would get that dx equals du over cosine x. Great. My next step said, okay, take what dx equals and replace dx in the integral. And this is where this one becomes my place where I know that I've run the wrong path, because when I do that replacement for dx, it should say du over something. It should help me. One of the most obvious ways of helping me is that it would simplify out the function that involves x. But can I cross off a denominator with an exponent? No, right? That would be like taking 1/2 x squared and crossing off the 2's, which you also can't do. Hopefully you knew that, right? Okay, so I can't do that, and what I've now done is actually given myself something even more complex, because now I'm looking at the integral of u times e to the cosine x times 1 over cosine x du. Okay, so that did not help anything. That's when I know that I've hit the wrong path, is when I go to insert that derivative here, and it's not simplifying this into something that I know how to anti-differentiate. Okay. So remind you then what we saw yesterday when we did this one, when they told us what to pick for u, and how at this point it became very obvious that we had picked the right thing because it simplified my function down to something a lot cleaner. Yesterday they said let u equal cosine x, which would be another obvious choice in this one, especially as we think ahead. You always want to keep in mind, what is its derivative? Is that something else I'm seeing in there that could help me? And sine and cosine are derivatives of each other, right? So that is obviously ones that we would want to pick. So then our function, or our integral, became sine of x e to the u. We did our derivative over here, and again, we did all of this yesterday. We solved for dx, and the difference at this point, when we went to insert that in, is now I have a sine of x here that would simplify with my denominator sine of x, and I see something simplifying. That's a good indication that we picked the correct function for u, or a helpful function for u. And then we want to make sure we don't lose any constant or negative, so we slid that out front. And then we were down to e to the u du. And if at this point this looks like something that I can anti-differentiate, we're sitting good, which it is, right? Derivative of e to the u is e to the u. The integral of e to the u is e to the u plus c, right? So we have that minus e to the u plus c. And our last step is to replace u with what u equaled, e to the cosine x plus c. Okay. Questions so far? The left should look familiar because we already did that problem, right? And by left, I mean right. So this one, could we have accomplished the integral without using u substitution? Absolutely. We've done it. It would have been thinking backwards through chain rule, which we can do. It's a little bit difficult when we have to do chain rule. So I like u substitution when it involves chain rule because it can kind of take the chain rule backwards thinking out, right? We will get to some that we really couldn't do without u substitution. And so we're, like I said, kind of starting with the basic ones, working our way up to the more complex. Okay, so let's talk about then, now this general statement that I have here, which is a very non-mathematical, this is just my thoughts on the board, things that you could do to, like, in general, help you think about what do we pick for u. Let u equal a function that's a derivative will make the other function go away. If you can think that far ahead, that's a great way to pick u. So if you can see something up there that, oh, if I took the derivative of that, that matches the other function in there, that's a good choice of a function to pick. That's not always going to be the case, but that's definitely one to look for. Other places that I would look for a u option would be insides of functions. Doesn't always work. Denominators of fractions. Again, doesn't always work. But those would be places that I would start looking to see if that would be a good option for you. Okay. So let's look at another one. Given the integral of x over x squared minus 4 dx, we're going to do this one by u substitution. I want to just kind of walk you through, as we look at this, how can I even find the functions that can be replaced with the letter u? Remember, functions can be any like polynomial, monomial, or the things we're looking at up here. We would not let u be the whole thing. So like if we went back to our first example, u is not going to be sine x e to the cosine x. Okay, that's not going to be u. It's not going to be the entire f of x that's in there. It's going to be some part of it. So as we look at this, we're not going to let it be the whole fraction. But maybe here are some options. It could be, see that x sitting up in the numerator? That's an option, right? That's a function. There is the denominator, which you can look at it as a couple different functions. You could look at the denominator as just that first term as x squared. You could look at it as the entire denominator, x squared minus 4. So as we think about the derivative of each of those, and will it help me in the long run, first of all, what is our derivative of x? 1, right? Derivative of x squared? 2x. 2x. So these two actually have the same derivative, don't they? Okay. This one, the derivative is 1. Is that going to help me simplify anything in the long run? Now this, again, not a official rule, but usually not going to help us to just exchange one variable for other. So instead of writing x, writing u is not usually going to help us much in this. So if you're just replacing one letter with one other letter, not really probably going to do much. These two, when you guys were talking to me about this derivative, did you notice that the derivative is similar to the other function in that problem? But also, did you notice they have the same derivative? So is one better than the other as an option? Absolutely. If two options that you have the same derivative, pick the bigger function. The more we can replace and take out of having to anti-differentiate, the easier the evaluating the integral is going to be, right? So that's why I would pick on this one the x squared minus 4 and let u be that entire denominator. So first we're going to identify what we're going to let u equal. And then I just show that. Okay. And then we think about, okay, what's the derivative of u with respect to x? Solve that for dx. And then come over here and replace dx. Look for something to simplify. Which it does. All right, we've got an x in the top here and an x in the bottom. Be careful when you do that simplifying that we don't lose the 2. What number am I actually sliding out front of that integral? 1/2, right? Don't forget it's actually in your denominator, so I am sliding that out front because the more I can get out of the way as far as doing my integral. I don't want to have to think about 1/2u or 1/2 times 1/u. Just slide that out of there. Multiply your answer by 1/2, right? Then we got to think backwards. This one was in our notes yesterday, right? The integral of 1/u, natural log. So we still have the 1/2 sitting out front, natural log, and then we talked about because of the domain restriction of natural log, putting those absolute value symbols. And we can look at, do I really need them or not, here in just a second, after I have now replaced u with what it originally equaled. And u was x squared minus 4. On that answer, the natural log of absolute value of x squared minus 4, do I have to keep the absolute value symbols? Can x squared minus 4 ever be a negative number? Yes. Had my original function been an x squared plus 4, do I need the absolute value symbols? No. Now, if I had left them on there and it was an x squared plus 4, is it wrong? No, it's not wrong. We did see one time, and I just want to continue to remind you as we think about little tips and tricks as we head towards that AP exam, etc., is that sometimes it might simplify further if I got rid of those absolute value bars. For example, something like absolute value of x cubed over x, I cannot drop those absolute value bars and simplify, correct? But if I had something like x squared, absolute value of x squared over x, the AP exam would not have that because I don't need, that's redundant, right? X squared is positive. I don't need to say that it's the absolute value of x squared. So this actually would be x squared over x, which means it would be option A, or B or C, or D, plain x, right? Because that would simplify down to just an x. So understanding when those absolute value bars, now is that going to happen like maybe once on the whole test? Probably. But worth reminding us is that if I can drop them, I might be able to simplify further. So, okay, the last one we need to talk about is this. Integral of cotangent of 7x dx. Now, as we start doing this, again, I might have a lot of trial and error on my assignment, and that is okay. You might be able to trial and error in your head as you get more used to these. I gave you a suggestion of maybe looking at the insides of a function to see if that would be a good thing to pick for you. We actually do have a function inside a function on this one, right? We have a 7x inside of a cotangent. So could I let u equal 7x? Yeah. So if I looked ahead at this, right? Derivative would be 7. Okay, well, I can slide the 1/7 out front. Great. But what is the antiderivative of cotangent? What function, when I take the derivative of it, do I get cotangent? Right? Nothing, right? That kind of goes back to, do I remember my trig derivatives? Do we remember our trig derivatives? Have we been looking at our flashcards, right? We need to remember our trig derivatives because it's going to be tough if I don't remember what my trig derivatives are to know what function gives me a derivative that equals cotangent. The answer is none. Okay. Okay, so that was not a good option. Well, my only other option is the whole thing, which we already know is not a good option either. Okay. Well, guys, what it turns out is there's a trick. So let's look at our trick. The trick happens when we are looking at the integral of tangent or the integral of cotangent, which they are similar to each other, right? In fact, they're just reciprocals of each other. And the trick is this. We're going to replace with their trig identity. So for our notes purposes, just, so we take really good notes here, let's remind ourselves of what those trig identities are. Tangent in terms of a fraction of sines and cosines is what over what? Sine over cosine. Cotangent then would be the reciprocal. And so what we want to do is replace cotangent. Instead of writing cotangent in that integral, we want to write cosine over sine. Otherwise, guys, there's really not any way we can do that. You guys see how I did that? Cotangent of 7x. It is cosine over sine, but they should still have the same inside, but they both have an inside, right? So cosine of 7x over sine of 7x. Question so far? Now, I said something earlier in passing that might help us on this one. We basically have two options. We already know that 7x is not a good option. So now I'm narrowing it down to cosine of 7x or sine of 7x. And I said something that might help you pick which one. What do you think? Think cosine? Yeah? Sine? That's your two options? They'll cross off. Yeah, and by his reasoning, couldn't I kind of say the other way, though? The derivative of cosine is negative sine, and that would just leave it with a negative. Okay, but think about where that shows up when we do that derivative. Hasn't that always showed up in our denominator? Where are we going here? Denominator. And we've always crossed it off with something in our numerator. Yeah? So to make this easier, I would let u equal your denominator. So its derivative ends up the denominator to cross off with that guy that's still sitting up in the numerator. Okay? And again, trial and error. What if that didn't work? We would go with the other one. So I would let u equal the sine of 7x, which means its derivative is, dx is cosine, not cosine. What is the derivative of sine 7x? 7 cosine. Chain rule, right? 7 cosine 7x. So I'm going to replace sine of 7x with u. I'm going to replace dx. Oops, I didn't solve. Again, careful that we only cross off, that we don't lose the 7 sitting out front when I cross off my cosines of 7x. So again, do you see why I picked the bottom over the top? I get that their derivatives would match the other function, but it allowed me to simplify, and that's what we're going for, right? So I would slide that 7 out front. Well, the 7's actually a 1/7. We have seen this one now over and over and over recently, the antiderivative of 1 over u. Natural log of absolute value of u. And my last step, sub in for u, sine 7x. Two questions. Do I have to have the absolute value symbol around the sine of 7x? Can sine ever be negative? Yes. Sine oscillates between 1 and -1. The 7, remember, all the 7 is doing is changing the period length. So it's going to be 1/7 of a normal sine curve, width-wise. That has no impact on its value, 1 to -1. My second question is, without u substitution, would you totally have known that the antiderivative of cotangent of 7x was 1/7 natural log of sine of 7x plus e? No. So we're starting to get into why do we have to use these. Eventually, I'm not going to be able to look at that. I would not have come up with that without u substitution, right? We've got to have some things to help us through problems like that. All right. Assignment. I'm at points trying to help you guys move on because at some point you may or may not have somebody up here helping you through stuff. You may be reading textbooks. So there is one problem in your assignment that reading the example number 7 on page 340 will help you significantly. Let's work on practicing reading our textbooks too. So part of your assignment tonight is to start by reading example 7 and then go through your assignment, and you should see one of the problems that is similar to that can help you.